Again, based on conductivity, we can say that materials can be classified into two categories, that is conductors and insulators. Semiconductors can be classified into an intrinsic or extrinsic based on their constituent elements. Either the spin will be different or the orbital will be different or some part of their characteristics will be different. Semiconductors are materials which you are hearing for the first time, which means that you might not know a lot of semiconductors. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we are going to start a new chapter here today that is all about electronics, and that particular chapter is semiconductor or simply semiconductor electronics. So let's see what semiconductor holds for us. So most priorly, before we start anything, we need to know what exactly a semiconductor is. And again, in the circuit world, we indicate a semiconductor like this, or simply a semiconductor diode. Diode meaning it has two ends. So again, before getting into what is a diode, what is the various types of diode, we need to know what is a semiconductor. So before getting into what is a diode, how it fits in a circuit, what are the peculiarities of a diode, we first need to know what a semiconductor actually is. So again, we can say that materials can be classified into conductors and insulators. So again, based on conductivity, we can say that materials can be classified into two categories, that is conductors and insulators. This is what you have studied until your high school lessons. But now we also know that high school is not the end and there is a lot of things we have to study. So just like that, we understood that there is one more category of materials which lie in between insulators and conductors, and that type of materials is known as a semiconductor. So what is a semiconductor? So we can just define a semiconductor simply as a material whose conductivity actually lies in between conductors and insulators. Those kind of materials are known as semiconductors. So to put it into broad perspectives, we can just simply say that semiconductors are materials whose conductivity lie in the region 10 raised to 6 to 10 raised to minus 6 ohm meter inverse. So if their conductivity lies in this particular region, we call it as a semiconductor. Actually, we can classify insulators, semiconductors and conductors based on how much their conductivity actually is. So in other words, mathematically, we can also represent what a conductor, or simply how we can classify conductors, semiconductor and insulators in terms of its conductivity. So again, this is how we normally classify objects, that is based on its conduction or simply conductivity. So again, how well a conductor conducts electricity, then we classify it as a good conductor. If it is really bad, we classify it as an insulator. And somewhere in the middle, which is having partial good conductance, but it is not up to the peak level of a conductor, that particular substances are known as semiconductors. So again, if their conductivities lie in this particular range, that is, if the conductivity lies 10 raised to 7 and above, we can say that, okay, that is a very good conductor. And if it is slightly less, we say that, okay, it's still a good conductor, but not as an effective conductor as these particular material ranges. And then semiconductors lie somewhere in the range between 10 raised to minus 6 to 10 raised to 6 ohms per meter, or simply ohm meter inverse. And insulators are materials who are very bad conductors, or simply they do not allow electric current to easily pass through them, like plastic, air, or even flesh. That is a very good examples for insulators. Now, semiconductors are materials which you are hearing for the first time, which means that you might not know a lot of semiconductors. So we can actually say that famous semiconductors include silicon, germanium, and any of the same group elements we can actually include as semiconductors. For example, the chips in your phone are actually made out of silicon. That is because silicon or germanium, because they are very good semiconductors. Now, again, why do we use semiconductors when we can use conductors? Again, that is the reason for the invention of semiconductors itself. Because if we use conductors which are very good conductors of electricity, if any of the parts are in touch with other parts, or simply if there is voltage level leak or something, then what happens? The entire circuit just lights up. So we don't want that. We don't want excess current to flow through any material. We want a definite amount. We want a definite control over the substances. And that can be achieved through semiconductors, which means that we don't want a huge level of conductivity. We only need a certain level of conductivity which can be achieved through semiconductors. That is the reason why in cell phones or in chips or CPUs, we don't use good like high grade conductors. Rather, we use very good semiconductors in most of the cases. Now again, we already know that how we can classify materials based on their conductivity, but that is not enough here. We have to introduce a concept which you have already studied in chemistry, that is energy band theory. So what exactly is an energy band? So we can just simply say that So what exactly is energy band theory? So energy band theory is just a theory we made up so that we can understand the excitation or behavior of certain atoms. That is, we know that atoms can excite their electrons to higher levels so they can conduct electricity. So for this to happen, the atom has to excite an electron to a higher state or to a more excited state. So based on this, we formulated that, okay, the energy difference between this is a considerable amount. So for that particular reason, an atom can only allow electricity to pass through it or conduct anything if that particular state is achieved. So for various atoms, this level will be different. For various elements, this level will be different. To understand this, to understand the conductivity of atoms, we actually formulated this particular theory that is known as energy band theory. So again, in an isolated atom, energy level of each electron is fixed. That is, we know that around the nucleus, electrons will be orbiting in a fixed state, right? In fixed stationary orbits. So again, they can only jump up or down if they receive a photon, or simply if they receive or emit a photon, then only they can jump up or down in that particular orbit, from that particular orbit. So that is the first consideration for energy band theory. And then we know that inside each crystal, each electron has a unique position. That is, they are restricted to their own orbitals. That is either p orbital or s orbital or d orbital, just like that. So no two electrons can occupy the same position. This you have already studied in your chemistry lessons as Pauli's exclusion principle, or simply as a part of VSEPR theory. So again, it just tells you that no two quantum materials, just simply saying no two fermions, that is two electrons inside an atom, can have the same address. Right. So either one quantity will be different, either the spin will be different, or the orbital will be different, or some part of their characteristics will be different. So that again is just mentioned here, that is, each electron will have a unique identity, so that no two electrons can occupy the same position. That will be a quantum anomaly, which is not basically possible. And finally, this particular energy band is categorized into low level energy band, and then valence level energy band, and just above valence level energy band there is conduction band. So again, this particular concept of an energy band is actually just there to help us understand how electrons help in conduction of electricity. So again, this is all imaginary, and you should know that there is no definite bands inside atoms. This is just there so that we can understand, grasp the concept of energy transfer, or just excitation of certain electrons. So again, how we imagine it is that there will be first a low level energy state. Low level energy state. So this particular band region is known as low level energy band region, and just above that low level energy band region there will be what is known as valence band. So what is valence band? Valence band is the band which contains all the valence electrons. Maybe just one electron, maybe two electrons, maybe three electrons, we don't know until we select the atom. So again, so the valence band is just simply the energy state or the energy band of the electrons which is in the valence shell. Or simply we can say that valence band contains all the valence electrons, and just above that valence band there is the conduction band. So how does an atom conduct electricity? So obviously this valence electron, that is the electrons in the valence band, has to reach the conduction band so that the electricity or the conductivity process can be completed. So in order to reach from here to here, it should have a definite amount of energy which can be given using a photon or any EM radiation of a particular frequency. If they get that particular radiation or energy, they will jump to the conduction band and they can conduct electricity. Then again, this particular gap, if it is more difficult to conduct, if it is less, it is very easy to conduct. If they overlap each other, then no need of doing anything, right? The electrons can just simply squish or just move around and they can reach the conduction band. So this distance actually matters. The distance is signifying that, okay, this element is very good at conducting, very bad at conducting, it is moderate at conducting. That particular difference, when it is laid out through energy bands like this, that is what is known as energy band theory. So how can you apply this to conductors, insulators and semiconductors? So how can we apply energy band theory to conductors, insulators and semiconductors? So very simply we can just say that the energy gap between valence band and conduction band is 0, which means that if this is the conduction band, this will be the valence band, which means they are overlapping each other. There is practically no distance between valence band and conduction band, which means that it requires no energy to move electrons up and down the conduction band. That is, from valence band to the conduction band, to move electrons there is not much hassle required, which means the energy requirement is minimum. That can happen at room temperature, which means that just by using the room temperature energy, that is, if it is at 28 degrees Celsius, that particular room temperature, that particular thermal energy is used for electron excitation from valence band to the conduction band. So that process is very easy. That is what is written here, that is, electrons move up to the conduction band at room temperature only. And finally, VB, that is valence band and conduction band, are both partially filled. That is, already there will be electrons like this. So we can say that some electrons will be in the valence band and some electrons will be in the conduction band, right? So it is very easy to move around the electrons from the valence band to the conduction band. Now what about for semiconductors? Semiconductors, the gap exists. That is, these two are not overlapping each other, but rather there is a small gap in between valence band and conduction band. But that particular gap is not too much when compared to the insulator elements. So we can say that there is a small gap and that particular gap is less than 3 electron volts. So, and we can say that only few electrons move up to the conduction band at room temperature. That is, only 1 or 2 electrons, maybe some electrons, only a few electrons can actually move from the valence band to the conduction band using the thermal energy that is available at room temperature. And finally, the valence band is completely filled. So it is completely filled, and maybe sometimes the conduction band is filled, sometimes the conduction band is not partially filled. It all depends on which element you are actually choosing and what you have already done with the element. So, and finally, there is insulators. Insulators meaning there is a large gap and obviously it is more than 3 electron volts and no electrons move at room temperature because the gap is too much. And then the valence band has electrons and the conduction band is completely empty. So basically it is not allowing any electrons to pass from the valence band to the conduction band. Now, since we have seen how we can classify conductors, semiconductors and insulators based on conductivity, we also have to study what semiconductors actually are. So we know semiconductors in terms of bandwidth or simply in terms of conductivity, but you have to also understand that semiconductors can be further classified. Semiconductors can be further classified into intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors and extrinsic semiconductors. And then again, this extrinsic semiconductor can again be classified into N-type, N-type and P-type. Or just we can say that the negative type and the positive type. So here we are going to study what is intrinsic semiconductors and what is extrinsic semiconductors primarily. So what is intrinsic semiconductors? Again, it is a classification of semiconductors. Semiconductors can be classified into an intrinsic or extrinsic based on their constituent elements or how they are made up. So what is intrinsic? Intrinsic semiconductors means that they are pure semiconductors. That is, they do not have any other material rather than the pure semiconductor materials they are used to be made with. That is, if you are using germanium or silicon or any atoms like that, the entirety of this particular semiconductor will be made out of germanium or silicon. That kind of semiconductors is known as intrinsic semiconductors. If you mix anything else with that particular atom, that is, if it is germanium semiconductor or silicon semiconductor, if you add any other impurities or if you add any other dopants to increase its conductivity, to decrease its conductivity, then it is known as extrinsic semiconductor, because we are tampering with the natural abilities of that particular semiconductor. We are enhancing or we are changing or modifying that particular semiconductor. That is known as extrinsic semiconductors. And based on its reaction, that is, if you are doping it with, again, I'll tell you what doping is. If you're adding impurities of certain kind, it can be turned into a positive type semiconductors. And if you are adding impurities of a certain other kind, you can turn it into a negative type semiconductor. So based on how you are actually adding impurity, and it is very simple what you are adding. So based on that particular thing, the semiconductor has two different outcomes again. So that is N-type and P-type. Now we are going to be focusing on what is intrinsic semiconductors. So again, intrinsic semiconductors are simply the purest form of semiconductors, which means they only have the atoms that is used to make them up. For example, here I am using silicon only to make up a semiconductor, and I am keeping it under a strong microscope and I am observing, okay, what are the atoms, what are the bonds, how it is actually forming. So this is the particular structure I will be obtaining. That is, only silicon atoms will be present. And since silicon has only a valency of 4, it means that there will be 4 electrons or simply 4 atoms surrounding this particular central silicon atom. Or much more precise way to say that will be, silicon has a valency of 4 and these 4 electrons will be shared with 4 other atoms in the vicinity, which will give it, that is, even if it is germanium, even if it is silicon, since it is a 4th group element, only 4 electrons will be available as valence electron, which means that these 4 electrons will actually be covalently shared, or simply they will form a covalent bond between the neighboring atoms. So that is why these 4 atoms are covalently sharing the valence electrons. 4 valence electrons are being shared among the 4 atoms, which also gives this particular semiconductor, that is this intrinsic semiconductor, its iconic diamond-like structure. You can see it is a diamond-like structure. If you have played cards, you know that what a diamond-like structure is. So again, this will give this a diamond-like structure, and this bond is achieved through covalent sharing of valence electrons. Since it is covalent sharing, we also call it as covalent bond, or in physics we just refer to this type of bonds, that is the sharing of valence electrons, as a valence bond. A valence bond. So again, it is covalent sharing, but we just call it as a valence bond. But still the question is, how do they conduct electricity? So again, I'm telling you, this is the structure and this is how the atoms are actually woven into the fabric. So again, the fabric doesn't mean it's in a cloth. It means that the structure of that particular semiconductor, that is the silicon based semiconductor, will be made out of this particular shape, that is the diamond shapes. So again, how does it conduct electricity? So what happens is that when they have enough thermal energy, let's say that there is enough thermal energy. When there is enough thermal energy, or simply Q, in thermodynamics we say that Q is heat. Just know that if there is enough thermal energy given to this particular system, what happens is that the electrons will absorb that particular thermal energy and they will leave that particular atom. So when an electron from here leaves this particular atom and goes here, what happens? Then automatically this central atom is with a deficit of an electron and this particular atom is with an excess of electron, which means this will again share it to the next atom and this will be shared to the next atom. Like that, the sharing process will keep on happening, which means that there is subsequent positive and negative charges being created, which means there is a potential difference being created. So whenever this positive charge is created here, the very next atom will actually donate one electron, filling in that particular gap. So this particular process just so happens to be like a hole formation and the filling of that particular hole. That is, if there was an electron here initially, let's say that that electron jumped to the immediate vicinity, which means there is a gap here formed. So this particular gap is now being called as a hole. Since it is absence of an electron, the hole will be positively charged, which means that the electron jumped away and a hole was formed there, and that is positively charged. And since there was a hole that is created here, the very next neighboring atom will donate its electron here, filling in the hole, thereby cancelling the positive charge. But by in doing so, the very next atom that is here will now gain a positive charge. So the very next atom before that will donate the electron, and this will actually go in a pattern, which means electrons and holes are being created. When holes are created, electrons are donated, filling in that hole, which means another hole is created, which means it is filled again. This process continues and the electrons are running around, which means there is conduction. So this will produce conductivity in intrinsic semiconductors. So again, what is intrinsic carrier concentration? So again, intrinsic carrier concentration just means that which one of the carriers is responsible for the conduction or simply the process of conductivity. So again, what is a carrier? Here we can say that the carriers are referring to the electrons or the holes which is responsible for the production of electric current. Since here, when one hole is created, one electron is donated in order to fill that hole, the number of holes generated and the electrons produced are both equal, which means when an electron leaves, one hole is created. One electron will fill that gap. So always the number of holes and the number of electrons will be remaining the same only. There is no excess or simply magically something cannot appear inside that particular intrinsic pure semiconductor. So we can say that the intrinsic charge concentration, which is indicated as Ni, will be equal to or is responsible or is created by the number of electrons, or simply the charge carriers are number of electrons in them. The way electrons move, it produces electricity. But wait, this particular electron concentration is actually also equal to the number of hole concentration. So we can just say that in an intrinsic semiconductor, the intrinsic carrier concentration of number of holes and number of electrons will be equal to each other, which means they are equally responsible in order to produce electricity or simply conductivity. Now again, at equilibrium point, that is, if all of this is at equilibrium, the holes created will be very soon will be filled with electrons and that particular process will stop. But what if I provide an external electric field? If I provide an external electric field, the story changes. Since now an external electric field is generated, the electrons will be moving in the opposite direction of the electric field. So if I create an electric field, then the electrons are jumping in the opposite direction, which means from here to here, one electron jump, which means a hole is created. Now, again, one electron right next to that will fill that particular hole. But then this electron will jump to the very next atom, creating a hole here. But okay, this particular electron can fill that particular hole. But then again, from here to the next atom, it will jump, which means a hole is created here. Again, if you focus on these particular creation of holes, we know that a hole is created as we move along the electric field, which means that holes are created here. Or another sense, we can just say that when we apply an electric field, positive holes are created. Positive holes are created, meaning positive holes are created and they are being filled, which means holes are appearing to move. They are not actually moving, but holes are appearing to move in one line, which means that it is positive charges which are moving. Simply, we can say that since it is holes which are moving, it is known as hole motion. And this particular hole motion can generate electric current, that is known as hole current, which is indicated by IH. I meaning electric current, and since it is produced by the hole motion of the positive charges or simply positive holes which is being produced, it is known as hole current, that is IH. And you have to also understand that there is already the current that is also produced by the electrons. So we can just call that as IE. So there is already the hole current which I just explained, and we know that when electrons move, it produces a particular current. So that is IE and IH. So these together in a semiconductor, the sum of hole current and electronic current together will contribute to the total current, that is I. So when you are measuring current in a semiconductor, depending on what type of semiconductor it is, we can see that the current produced will be a result of, will be a sum of the electronic current and the current that is produced because of the hole motion, that is known as hole current. And you have to understand that since this particular conductor, that is intrinsic semiconductor, has no impurities in it, it is absolutely pure, which means that in conductivity terms, that is in terms of conductivity, thermal energy influences intrinsic semiconductor. If you give it more heat, more current will be produced. Depending on the ambient temperature, the conductivity of the intrinsic semiconductor actually varies, which means that if temperature is decreased beyond a level, then we can say that the conductivity also decreases, or simply we can say that theoretically at absolute zero or simply at low level temperatures, the intrinsic semiconductor will behave like an insulator. So an intrinsic semiconductor will behave like an insulator under ambient conditions, or simply when temperature is very low or very close to zero. That was all about intrinsic semiconductors, but what about extrinsic semiconductors? Obviously, intrinsic semiconductors means they are very pure, which means extrinsic semiconductors are not so pure. It means that instead of just having silicon or germanium, we add impurities to that. Instead of having just one type of atom, we add impurities to that particular atom, so its levels are enhanced or modified to fit our own needs. So this particular modification can be done by adding impurities. So what is this impurities? Impurities meaning other elements, other atoms. To say it more precisely, it should be very close in the size of the actual atom, which means we will be doping it with, or simply we'll be adding impurities to this particular pure atom from the very next or very before groups, that is succeeding or preceding groups. So either if these are both fourth group elements, so these are fourth group elements. So if we are adding impurities, we'll be either adding a third group element or simply a fifth group element. So again, if I'm adding a third group element, there will be 7 electrons. If there are 7 electrons, it is not having 1 electron to complete its valency. So it is just shy of 1 electron, which means that it is partially going to be positively charged. Okay, and if I am doping it with a fifth group element, then there will be an excess of 1 electron. That particular excess of 1 electron means that it is going to behave negatively. It wants to just get rid of that particular electron. So again, this particular behavior will give it its positive type and negative type, that is p-type and n-type. So again, I'll explain what is p-type and n-type very soon. But for now, what is extrinsic semiconductor? Extrinsic semiconductors are semiconductors in which impurities are added so that we can modify their natural conductivity. So if we add impurities to semiconductors, it is known as doping. So the process of adding impurities to a semiconductor is known as doping. That particular process is known as dopings, and the elements which are being added, for example, third group or fifth group, that particular elements are known as dopants. So that is known as dopants. So simply we can say that doping is the process of adding dopants to semiconductors to enhance their performance. That particular concept or that particular process is known as doping. So again, finally, you just have to remember one more thing, that is when we are doping, that is when we are adding impurities to this particular semiconductor to make it an extrinsic semiconductor, there is two things you have to remember. That is, we cannot add impurities as we please. We cannot just add gold or zirconium to germanium and expect it to be an extrinsic semiconductor. There is a couple of rules that states that the dopant should not disturb or just simply distort the lattice structure, which means already there is a lattice structure. You have already studied about what is lattice structure, what is Bravais lattices and all that. So I'm not going into the depth of that particular thing. So again, it should not disturb or distort. It should not change that particular lattice structure. If it has a cubic structure, you cannot directly come here and change it into a hexagonal structure. You have to make sure that the dopant does not change the crystal lattice structure. And then the dopants and semiconductor atoms, that is whatever you're doping it with, whatever your impurities you are adding, that particular impurity, the atoms should have very similar sizes. For example, if you're doping germanium or silicon, it should be having almost very similar sizes, which means that similar sizes or equal sizes. For example, if you're doping germanium or silicon, that is why you're doping it with fifth group or third group elements like antimony, arsenic, that is like antimony, arsenic and boron, like that. We'll be adding different type of materials which are almost same in size. So that should be observed. And again, since we are adding fifth group or third group elements, we can simply say that we are adding pentavalent elements or trivalent elements, which means the valence band electrons, that is the valence electrons will be 5 in the fifth group and 3 in the third group, which just says that, okay, if you are adding an atom which is having 5 electrons in the 5 electrons as the valency, we just say that, okay, that is a pentavalent atom or pentavalent dopant that is being added. If it only has 3 electrons, if it is a third group element, we say that, okay, it is a trivalent dopant that is we are adding. So again, that is all for today, just an introduction into semiconductor electronics. In the coming classes, we'll learn a lot more about semiconductors. So until then, I hope you have understood everything about semiconductors, including the extrinsic, intrinsic, and other properties of semiconductors. Until next time, thank you.